So this is not a talk to get you to fall in love with nerves. I think Justin did a great job of that earlier. Some of the stuff that's going on even with the core team that I'm not aware of, even though I'm on that team, is just fantastic. There's a lot of work going on there. But this isn't to get you to love nerves. In fact, amazing languages like Elixir and frameworks like nerves are not the reason that we write software. Software isn't there just so we can write it. Nerves doesn't care what we do about it. Elixir it's not aware of the things that we're building with it. We do things in Elixir and we do things in nerves so that we can change the world. We want to change the outcome for people. And in his book, User Story Mapping, Jeff Patton writes, "We measure what people actually do differently as a result, as a consequence of what you've built. And most importantly, whether you've made their lives better, the world is different for them. Sometimes the way we change the world is subtle. It's hard to perceive. Other times, the impact is obvious and powerful." So how this all started, 12 years ago, the world was very different for my wife, Amanda. She's sitting right here as moral support for me today. This is what she looks like. She had just learned from her doctor that she had diabetes. The doctor who made the initial diagnosis was not equipped to educate her about the diagnosis or diabetes. It took months to get her in to see an endocrinologist. It was a scary and dark period for her and for me as well. So with little more than a few words from her doctor to check her sugar and don't eat carbs, like that's actually realistic advice that you could follow, Amanda had to bootstrap everything she knew about a disease that would define the rest of her life. Think about that for a minute. Put yourself in her shoes. You go into the doctor because you're always thirsty and you never feel very good. And you learn that your life is forever altered. Worse, the doctor may not even have enough time or specific knowledge to help you understand what you need to do next. So I have about maybe twice as long as a doctor visit today with you. And I'd like to walk through some of the basics of diabetes before we get into the technology. So what is diabetes? This is how things are supposed to work. When you eat, your body breaks down the food into something called glucose. It's basically sugar. That glucose enters your bloodstream and causes your blood glucose to rise. Your pancreas senses the glucose and produces insulin. It's a hormone. Insulin is the key that unlocks your body's ability to convert and store energy. As your body uses that insulin, the amount of blood glucose drops. On the other end, in between meals, your blood sugar may begin to drop to unsafe levels. This is for healthy people as well. I've had a couple of lows as I've been going on with this. But your pancreas senses that and produces something called glucagon. Your liver and your muscles sense that glucagon and release extra stored energy that they have into the bloodstream, and your blood sugar rises again. So what happens when this all breaks down? There's two types of diabetes. Let's look at type 1 first. Type 1 is an autoimmune disease. It's when a person's pancreas stops producing insulin, a hormone that enables people to get energy from the food. It occurs when the body's own immune system attacks itself and destroys the insulin-producing cells in the pancreas called beta cells. Type 1 has also been referred to as juvenile diabetes, although you can get it at any age. Type 2 is a metabolic disorder. It's a more common form, and it's that your body is actually still producing insulin, but it can't actually process the insulin that it produced. Both forms of diabetes are a little bit more complicated than that. There's some things that kind of cross over between 1 and 2, but I'm not going to get into those details today. So the summary so far is everybody needs insulin in order to turn glucose into energy. Diabetes is a condition where your body either doesn't produce it or does produce it, but can't handle it. So at first, Amanda was misdiagnosed as type 2. It's pretty common among people with type 1 because type 2 is so common. She eventually received the correct diagnosis as an insulin-dependent type 1 diabetic. For the rest of the talk, I'm going to kind of put type 2 aside and go back to type 1. So what's a key fact here? There's nothing that you can do to prevent type 1 diabetes. At present, there's nothing you can do to get rid of it. Type 1 is often misunderstood. Insulin was discovered at the beginning of last century. The insulin that diabetics use now is faster, better than anything that we've ever had, but it's important to understand insulin's role in the whole process. Insulin is not a cure for diabetes, it's a treatment. Frederick Banting said, "It enables the diabetic to burn sufficient carbohydrates so that proteins and fats may be added to the diet in a sufficient quantity to provide energy for the economic burdens of life." That's a mouthful. But he figured out basically that insulin is very important for us to be able to convert our glucose into energy. There's a stigma often with diabetes that it's somehow your fault that you caught it. With type 1 specifically, It's an autoimmune disease. People who struggle with this deserve our empathy. They deserve compassion, not judgment. So what happens to your blood sugar when you have diabetes? When you have high blood glucose or hyperglycemia, our bodies are in the process of not being able to convert that glucose into energy. It builds up in the bloodstream. Over the long term, high blood glucose is deadly. It raises the risk for heart disease. It can affect your eyes. It can cause you to go blind. It hardens your blood vessels. It damages your nervous system. It can cause kidney failure and even affect your teeth and your gums. It's pretty bad. In extreme conditions of no insulin, where the body can't get any energy from the blood glucose, it will begin to break down stored fat and muscle instead. It releases a toxic acid called ketones and can induce a diabetic coma. On the other end, blood glucose, when it's low, is called hypoglycemia. When you have too little glucose, there's not enough energy to keep your body running. It's like your battery's low. It's very dangerous even for a short period of time. You lose your ability to think straight. You become dizzy or you become lightheaded. You lose consciousness even, along with the ability to take any kind of corrective action for it. Without that ability, your vital organs will just shut down. Your brain can't function. That's deadly. Diabetes isn't all about just food and insulin, though. It's affected by many things. It's sleep, stress, anxiety, other hormones, hydration, physical activity, medications, caffeine, even illness. Public speaking can even indirectly affect your blood sugar. So a person without diabetes will tend to have a blood glucose average in the 80s. You'll see that in a little bit. I'm wearing a CGM right now, so we'll be able to look at my blood glucose in a little bit. Someone with uncontrolled type 1, though, they'll have wild ups and downs, and it can happen very quickly from a high to a low. So let's talk about how insulin is delivered, both in a healthy person and in somebody with type 1. When a healthy pancreas produces insulin, it has two basic modes. It produces a large amount of insulin when we eat food, and that's called the bolus, essentially. Our bodies are amazing. Those of us who don't have type 1, our bodies are amazing. Your pancreas can sense how much insulin it needs to deliver almost before you even eat the food. And so it's counteracting the food that you're eating. I tried to make my blood sugar go high this week, and I've been failing at it miserably. I've been drinking sodas and doing all the things that you should never do if you're diabetic, and I can't even get it like above 120. Now, a lot of people with type 1 are probably angry at me for even saying that, because that would knock them up to 400 or 500. But our bodies are amazing when it works correctly. So, but a person with diabetes has to do the math for how many carbs they're eating. They have to figure out how much insulin to deliver. It's not a science. You're out to eat at a restaurant, you have no idea how many carbs are in the food that you're eating. You can kind of look at it and guess, but you're going to be wrong. So anyway, when you have type 1 and you're delivering the insulin for the meal that you have, it's called a bolus. You basically go on your insulin pump, or you go to your needle that you inject with, and you calculate how much carbs you're eating, how much your blood sugar is right now, and you deliver a lot of insulin for the food that you're taking. If you want to think about it like a mnemonic device for that, that would be like a bowl of food is a bolus. In between meals, your pancreas also produces like a background drip of insulin just to kind of keep things going. For a person using an insulin pump, this is called a basal rate. So a bolus is like one, no mouse there. So the bolus is like the top of that curve. That's generally measured just in units, like there's no time component, even though it takes time to deliver that. A basal is like a units per hour kind of a thing, and it just goes in the background. So you might have a basal rate of like 2 units per hour, but you might bolus 6 or 7 units for one meal or more. So I want to talk a little bit about the diabetes technology that's available right now. So I'm going to try to switch to a camera here and just give you an opportunity to see. All right, so first up we have an insulin pump. I actually have a very stylish pink insulin pump right now. And this usually has a little cannula tube that connects to your body and goes right underneath your skin. It has a small motor and a small computer on it, and a reservoir of insulin, and there's a motor on it that basically just twists the right amount to dose you the right amount of insulin. It's a very precise dose. There's a blood glucose meter, which I actually don't have up here. It's the thing that you usually see on TV when they talk about, how you have to check your blood sugar a lot. There's a little like pinprick needle. Oh, hey, thank you. So there's some type 1s in the audience with me today. This is a blood glucose meter. So you basically prick your finger, and then there's a test strip that goes in the one side of it, and then the other side. And it will tell you what your current blood glucose is. You need that, even if you're using some of the higher technology stuff like continuous glucose monitors, you still have to calibrate these things about once every 12 hours with the blood from your finger. And then there's also a continuous glucose monitor. It's a device that indicates your blood glucose. It's not measuring blood glucose directly, it's measuring a proxy variable for that. And then it basically needs calibration periodically to say, okay, what is your actual blood glucose? And it does a correction factor for that calibration. I'm going to show you what, I'm actually wearing a CGM right now. This is the Medtronic Enlight sensor. And if I can get the lighting right here, you can kind of see, it's like kind of like a seashell or an egg, maybe. And those things basically every 5 minutes transmit your current blood sugar over to the insulin pump or whatever CGM device you're using. Okay, enough of my face up on the screen there. So I'm going to talk a little bit about looping. When you're talking about type 1 diabetes and technology, looping is an interesting and very important concept. When you're dealing with type 1, technology like this is hard. It requires a lot of thought, active monitoring. One of the people in the type 1 diabetes community, when they're not closed looping, calls this manual diabetes. It's basically you actually have to do all the math and you learn how to do this stuff in your head as time goes on. But after a while dealing with manual diabetes, you kind of want to move beyond that. You don't want to have to think about that anymore. So the question came up, if we can continuously measure blood glucose with a CGM, and we can deliver precise amounts of insulin via command to a pump, why can't a computer do this for us? Why do we have to do all this math as humans and with mistakes and poor understanding of some of this? So the idea of a closed-loop artificial pancreas was born. I will note that Medtronic actually has an FDA-approved closed-loop insulin pump out right now. It's taken a very long time, decades for some of the people in the community who've had type 1, waiting for the FDA to approve something and for Medtronic to come out with it. So there's a lot of development and regulatory phases that are going on. There's still a while before people are going to have like easy access to the pump because of insurance and other reasons like that. So while people were waiting for this to happen, and while they're still waiting for it to happen, there's a whole community of reverse engineers and scientists, hardware and software developers, and people with type 1 working together to create an open source closed loop. So what is a closed loop? It's a very important concept. It has 3 phases. There's a monitor phase, and in the monitor phase, there's a computer that basically just gathers information. It pulls in all of the relevant information from your pump and from your CGM and gets everything that it needs in order to do the next phase, which is prediction. It's basically trying to predict the future. It's going to fail at it, but it's not going to fail at it as bad as we would if we do it manually in our head. So it goes out about 30 minutes. The idea with the prediction is that you want it to be you want it to be something that people can understand. If it's predicting that you're going to go low, but you know you just ate food and you're going to go high, then the algorithm is going to confuse you and you're less likely to use a closed loop. So the prediction algorithm is, there's no machine learning, there's nothing really fancy going on in there. It's exactly the same kind of math that you would do in your head if you had constant ability to just stare at your CGM and go, okay, I think I'm going up. And then the final phase is the control phase. And because the loop is, based on the prediction that the closed loop will send a command to the insulin pump to change the basal rate. Now, we talked about that a little bit. I'll just reiterate. The bolus is like one that you would do at a mealtime. It's a lot of insulin. The basal rate is just a background drip. So if it sees that you're going to go high, it will up that background drip a little bit so that it counteracts that. If you're going to go low, it'll go all the way to cutting off insulin. This is really important if you're in the middle of the night and you're starting to go low. You're not thinking about your diabetes. You're asleep. You're dreaming, hopefully. And it's just saying, okay, it looks like you're headed low. You're going to go, okay, I'm going to cut off insulin. That's a huge factor for Amanda and me. That was really important for us and has really transformed our sleep. Because the loop is only changing that background basal rate, you can out-eat it. You can eat a candy bar, you can eat a glucose tab, you can do something, drink a drink, and you can actually counteract the effects of the algorithm if it's doing something you don't understand or doing something wrong. That's the key safety feature of all the closed loops that are out there. But a lot of people say, isn't this like unsafe? You're changing medical devices and things. The key safety feature is that you can out-eat it. So current looping technology. There are, I think, like basically 3 that are available within the open source community that people are using right now. One's called Loop. It's an iOS device. I've worked with that one a little bit. I actually wrote the CGM decoding for the Loop app. Amanda's used that before. It's pretty cool. There's an Apple Watch app. You can tell it I'm eating tacos, and it actually delivers insulin differently than if you tell it that you're eating pizza. Pizza is like the worst. There's also one called Android APS. I know literally nothing about it. It's got Java. It works with a different pump than I'm working with. So it's another option. I think it's more popular internationally right now. And then there's one called OpenAPS, and it runs on a Raspberry Pi or an Intel Edison. It uses Python and Node and JavaScript and stuff. OpenAPS is the most popular. It's the one that Amanda's currently using. By the way, after this talk is over, feel free to come up to me or Amanda. We have all the geeked out toys and stuff. We've built many rigs, and so we understand a lot of this stuff. Some of the stuff we've iterated on is really cool, and I think most people would be interested in it, even if you don't have type 1. So it's made up of a full Linux. OpenAPS is a full Linux operating system. There's Python packages that you have to manage dependencies for. There's a special wireless chip from Texas Instruments you use. It uses Node.js for the prediction and control part of the loop. There's cron jobs. There's an internet reporting tool called Night Scout, and that pulls it all together visually. If any of what I just said doesn't make any sense, just replace everything with it's complicated, and you've got the gist. In order to start looping, it takes a long time. You have to learn about all the moving pieces. You have to have somewhat of a technical background for it. You have to have the right version of Linux installed. You have to know how to SSH and use Git. It actually uses Git within the loop to commit, like all the loops do a Git commit so that you know what happened the previous 5 minutes. So it's pretty deeply technical for a health technology. Things have come a long way since then. There's a lot of work on the setup scripts that are happening and everything, but it's still kind of a daunting exercise to get up and running with it. So even when things are configured correctly, closed loops have a lot of technical challenges. Wireless communication with a pump is flaky. You can kind of maybe see I have the pump right next to this computer running the Elixir code because these insulin pumps are not tuned with their wireless. They could theoretically transmit across the room and it would be fine, but the wireless antennas and everything that they have tuning on these things is not very good. So I have them literally inches away from each other so that it works. Batteries die, network connections come and go. Computers that travel where we go have the same kinds of problems as we have when we travel. And so when I was learning about OpenAPS with Amanda, I couldn't help but think, what if we didn't have to know all of this in order to start closed looping? What if we could focus on the loop algorithm and how it works instead of all the Linux system administration tasks that go with it? I'd been doing work with Elixir and learning about it. I learned how it's fault tolerant, that it could recover from flaky wireless communications and drop network connections, and it was surprisingly simple. At the same time I was learning about the NERVS project, Greg got me involved with it. Garth Hitchens, just the whole community of the NERVS core team got me really excited about what was going on there. I could build an Elixir application where NERVS took care of all of those details of loading it onto a tiny computer, giving the application total control over the hardware. That's one of the big problems with the OpenAPS algorithms. They have to basically contend for the devices. They have a full Linux operating system that could be doing other things with it. And so where closed looping was pretty weak at the time, Elixir and NERVS were really strong. They complemented each other. So I began to learn more. I learned how to pull CGM off of an insulin pump. I learned how other history events could be pulled and decoded from an insulin pump. It was just an experiment at the time, just to see if Elixir could really handle the problems that I was told that it could handle, like binary decoding and wireless communication that's flaky. But not only was it capable, it was built for this problem. I gained momentum. I started to pull more and more information off the pump, the things that you would need in order to do a closed loop. Things were really moving, and then I had to make a choice. I kind of hit a wall. The core of closed looping right now in OpenAPS, I mentioned it before, is JavaScript. It's written in Node packages. And I wasn't sure if I should try to port that over to Elixir or if I should try to use it directly. So let me just stop for a second and talk about how I got involved in closed looping. Amanda learned about it first. She was thinking about it, learning about it, asking me questions. I had no idea. I didn't even want to look at it. It's kind of scary. And so she told me she wanted to close the loop, and I said no. She needed my help for it because it's got so many setup steps and everything. I said no, I didn't want that kind of responsibility at all. She asked again, and I said no again, but I said, hey, think about this. Like, really weigh the consequences, weigh the risks here, and if this is something that you really want to move forward with, come back in like a month and tell me the same thing. So she was thoughtful, she was deliberate, she weighed the risks. She came back to me and said, I really want to do this. And I'm married to her, I had no choice. So I fell into all of this, all the work that I've done over the last year and a half, because my wife made me. So for me personally, taking on the responsibility of writing that prediction and control algorithm, or even just porting it over, is too much to bear. I have really no desire to lay awake at night thinking about all the people who could be running on my code that might have a bug here or there and cause problems for them. So I decided that I was going to build a custom nerve system that pulls in Node and actually runs the closed loop algorithm from Elixir, basically shelling out the node. That actually worked. I don't know why I was surprised, but it was easy. Everything that I've done with Elixir and nerves, I feel like is a daunting challenge, and then I come out of it like an hour later, and I'm like, I'm done. So that's a testament to the power of Elixir and of nerves, and how build root and all the things that piece together and make all the system components come together. Like, it's just so amazing. Every time I push a firmware, I'm just thinking to myself, there is so much going on here, but it's so easy. So anyway, back to the present. Where are we? The first closed loop running on the Elixir and nerves project that I've started ran a little over a week ago. It evaluated my blood sugar. I'm not type 1. My pump settings predicted my blood sugar, sent a control command to alter the flow of insulin to the pump. It was a successful spike of what's possible. There's not a lot of tests around this or anything. And in fact, it really just altered my basal rate to 0, because it's like, you're fine. You don't need this. I am actually running a monitor-only CGM loop right now. I want to kind of show you that just so you can kind of see some of the technology behind this. So this is my current blood sugar as I'm giving this talk. Some people who have type 1 actually will see a spike in their blood sugar, but apparently my pancreas is awesome, so there it is. So the project supports only one of the 2 major CGM manufacturers right now. Amanda actually runs on Dexcom, and I am only supporting the Enlight, the Medtronic one right now. The hastily assembled closed loop code needs to be rethought and re-implemented with good attention to OTP architecture and things that are probably the weakest for me right now. I come into languages and technologies and frameworks almost always from a different angle from everybody else. So where everybody else might be coming at it from Phoenix, I'm like, okay, can I make a tiny computer blink a light? I think that's probably common to the Nerves core team, but it's definitely not something where I would have learned the OTP application structure first. I learned how to blink the light first, and now I'm like, okay, I need structure because I want to blink 2 lights. So that's kind of all of the background information, and I wanted to kind of reiterate the vision that I had when I was going along the OpenAPS project with Amanda. I was learning how it worked. I was daunted by it. It was just so hard, and I thought to myself many times, like, how does anybody actually do this? Like, how do you not have a computer science background and still loop? And so as I was kind of forming this vision in my head and trying to figure out where I wanted to go with things, I thought, what if you just plug a firmware, you burn a firmware to an SD card, you plug it into a computer, you go to a website and you configure your settings, and you're up and running on a loop. So that's really what's driven me through, actually, at CodeMash last year. That's what drove me all week to basically skip most of the sessions and get the OTG port working on the Raspberry Pi Zero. Is I wanted to be able to have that serial and Ethernet connection to the Raspberry Pi Zero so that I could see what was happening and drive some of this progress forward with this pump. And so I'm happy that I got to contribute some of that stuff back to the Nerves core team. It seems like it's popular. I don't know. But I want to demo a little bit here, just the ease with which I envisioned everything coming together in practice. So I just need a little bit of time to set up first. So what I'm going to do is go from basically 0, where I have a firmware that I'm going to burn onto an SD card. I'm going to start up a computer. Am I still coming over? Okay, I'm going to start up a computer with this firmware running on it, and I'm going to configure it basically from scratch and have a loop running in about, 5 minutes or so. All right, so this is just an SD card reader. I'm just going to burn the image to it first. Give it some font bump here. Okay. Type my super secret password. Okay. This part is actually what fascinates me the most every time. I just burned an entire operating system in my application onto an SD card. I mean, I've seen it probably 100 times or maybe even 1,000, and I'm still fascinated that it happened so quickly. All right, I'm plugging it into a Raspberry Pi Zero. The only, let me open QuickTime up again really quick and just show you this hardware. There's nothing really special about this hardware. It's just a chip that happens to know how to talk to an insulin pump. This company is now out of business, so I have to come up with a different plan for what I'm going to do in the future to support it. But there's nothing really crazy. It's just a Pi Zero W running this firmware that has a chip on top. All right. It's plugged in. Make sure I have the right one. Yeah. Some of this might look familiar to the earlier keynote. It's just doing a completely different thing with it. So it's taking that partition and formatting it now with ext. So now you know that I don't have any tricks up my sleeve. It's reformatting the app partition, so there's nothing that could really be configured now. So while it's doing this, let me talk a little bit about some of the challenges that I ran into. I don't have type 1. That's a big challenge for actually writing code to support people with type 1. I actually am wearing the CGM. I didn't have access to a CGM earlier. So I built this thing that I'm calling the Groundhog Day CGM. It's basically 24 hours of my CGM, but pretending like it's live. So as I ask the system, can you give me more CGM data, it will walk up to 5 minutes before now and give me just that much CGM. Even though it's like pre-baked and everything, it's pretending like it's live data and feeding it to me like it's live. So I can actually see the algorithm working. I can see it all happening without actually having to wear a sensor in my arm. Okay, so it's trying to loop, but it can't because nothing's configured. Let me make sure I'm on the right Wi-Fi. Okay. This is, for all you people who do Phoenix, I'm sorry. This is the basic Bootstrap application that I wrote for this, and it's ugly, but it works. I had to build in time zone support really quick this week because I just moved from Eastern time zone to here and everything broke. That was awesome. And the super secret pump number, don't pay any attention to that. And then the device that it's going to talk to over serial. Now I need some awesome Wi-Fi, so I'll do that. No, I don't need your help right now. Okay, and also just so you know that I'm not like trying to trick you at all, I'm actually going to use a different Night Scout. That host name I picked very delicately. If you can't read it, it says t1d.isveryevil.org. All right, so I just configured the loop. And because I'm not smart enough yet, it's just going to have to reboot the device to boot the new configuration. I would like to fix that, but I'm not ready. Okay, so here's the brand new Night Scout instance. There's nothing going on here. This is the reporting tool that I didn't write. It's written in Node and Mongo. This is what basically everybody uses to understand how their loop is working. So I wanted to make this look as much like OpenAPS as possible, so I need to interact with the same things that everybody else does. So assuming this all works, then in just a minute we'll start seeing my blood sugar show up there. Let me unplug my other rig here. And make sure that my Wi-Fi access point's working. Okay, move my pump over closer to it. I have notes, and I've just completely abandoned them, so let me go back to this really quick. Yeah, so I think Justin kind of highlighted it a little bit in the keynote, but one of the cool things about this is that there's so much room for people, even who don't understand hardware, to jump in and help with this kind of stuff. I mean, I have a Bootstrap application that's a single form, but you could see how, like, I could show CGM running on the device. I don't even need an internet connection to make this all work. You could actually build basically a replacement for Night Scout and put it on here. Only knowing Phoenix, you don't even have to know how Nerves works in order to do that and to contribute. That's really powerful with Nerves. Some of the other cool things that I did along the way, I didn't always have access to the hardware that would talk to the pump, and so I needed a way to pretend like I had a serial device that was talking to a pump, and I actually built essentially VCR, but for UART communications. And so I'm storing off in this comma-separated file basically all the reads and writes that happen between them so that I can replay it and say, this is what it looks like to read CGM from a Medtronic insulin pump. I'm not sure, there might be application for that outside of what I'm doing, but even if not, it's really cool to be able to capture and encapsulate the entire communication that's required in order to talk to a pump and do a closed loop. Oh, hey, look, it worked. Cool. I don't know, that's neat. The scary stuff that you see off to the right side there is all of the binary page protocol stuff that happens with history pages in CGM. And if there's time, I might go into that a little bit. When does the session end? How much time do I have?
14 minutes.
14 minutes. Okay, maybe I won't have time for that. So I do want to do one more thing. It's a little bit riskier, but hey, you know, why not? I'm up on stage. So that's the CGM monitoring only loop. You can kind of see I have all these lines of code. Well, you might not be able to see. Let me do a font bump here. And maybe some more font bump. Okay, so this is the loop. Right now you can see it's only doing Night Scout entries and Night Scout treatments. Entries are the CGM, treatments are like any finger prick calibrations or anything like that. I'm going to uncomment all of the crazy lines there that look up the pump history and save it off to a file, look at your current basal rate, pull the pump profile information like battery information, calculate the insulin that you have on board out, which is also a prediction thing. It wants to make sure that it understands how much insulin is still in your body and being absorbed. And then it's going to call determine basal and enact a temp basal on this pump. Now, if I had this thing hooked into my body, that would actually affect the insulin flow to it. So maybe this works, maybe it doesn't, but it's worth a shot. So let me just build a new firmware based off of that. Let me make sure I save that file too. Yeah. So while that's happening, there's a few things about Elixir and nerves that are really great for this problem space. One of them is Elixir's mentality of let it crash. Let it crash in terms of the technology and the hardware, not in terms of your blood sugar. Like, you really don't want your blood sugar to crash. But letting pump communication be flaky like it is and recognizing that and letting the loop just crash and then restart later is perfectly fine. That's exactly what we need to do. But I didn't have to write any code specifically to handle that case. I got supervision trees. They're doing their job. Everything just works. The Python code for OpenAPS has like error handling and exception handling everywhere, and it's really hard to parse and understand. So I'm really happy about that. It's still building. Maybe I can talk a little bit about the CGM pages that you were seeing up on the screen over here too. The way that these things are parsed is using binary protocol matching, or binary matching in Elixir for this binary protocol. And these pages are 1 kilobyte of data each. And in order to process them, they have a checksum. So you check the checksum, and then you actually have to flip the things around backwards because all the events that you care about are at the end because they're more recent. And so I have to flip all these things around backwards, process them in reverse. Some of them are different sizes than the others. So I'm parsing out the head, byte, the opcode to see if it's a CGM reading or if it's some kind of other event. And then all of that stuff just works. Like, Elixir was ready to handle this problem, and it just needed somebody to type the words into the computer. That's fascinating to me. And the fact that I did all that work and I was like, okay, this is cool. I pushed something up to Heroku and it worked and decoded some stuff. And then I was like, maybe this will work with nerves in like first try, like right in there. It was really cool to see all that stuff come together because I didn't do it. It was really just the frameworks and everything pushing me in that direction. All right, so I'm going to do a remote firmware push here. This is going to be exciting. I am going to update the running firmware over this USB cable that you can't see. This is something I think, Justin, did you do this in your keynote? Did you do a firmware update? Okay, I'm doing a remote firmware upgrade, and it's upgrading the partition that's not currently active as it's still running the loop. So there's two partitions, the A and the B. It's upgrading the B in the background while the loop is still running. And once it's done and checks everything out, it's going to reboot into the new firmware. The new firmware is the closed loop. The old firmware is just the monitor-only CGM that's running. And it's going slowly now because I'm up here on a stage. But slowly is still fast because that's an entire operating system getting dumped over a USB cable. Yeah, 30 seconds, no big deal. All right, so it's rebooting. And actually now it's rebooting. So while it's doing this, I'm just going to kind of let it go because I'm not sure if it's going to work or not, and so it's not useful to help just sit here and watch it. It maintained the configuration that I already put in there because it's a firmware update. So that app partition actually still has the configuration that I did in Phoenix earlier. So everything should just work, and we'll see. But let me talk a little bit about the future. How is this going to change the outcome of people? I haven't really connected that back. Like, this is all cool technology, but I started out the talk asking, how is this going to change the world? Like, how is what we're building, how is what we're doing going to change the world? Imagine if instead of having to have a computer science degree, you could just download this project and burn it onto an SD card and be up and running. I mean, imagine if in seconds, instead of weeks, you could be up and running on a closed loop. And you could spend all of your time thinking about that algorithm and trying to understand exactly what that prediction is doing and managing your own disease rather than trying to manage cron jobs and SSH and firmware updates and everything. What if you didn't have to know Git in order to loop? I mean, that's kind of crazy. The results of this are pretty personal and pretty dramatic. Amanda's A1C, so the A1C is like a weighted 3-month CGM reading. Her A1C went from 7 to 5.8. To give a reference of that, a person without type 1 will usually have an A1C up to about 5.6. So she's basically almost not diabetic in terms of the outcome of this. Her roller coasters of highs and lows, which the A1C doesn't really show you, have also been less. Like, we sleep at night. That's kind of great. I don't have the lows and the highs alarms in the middle of the night that she sleeps through. So I'm not the one waking up and like flailing my loving arms at her, trying to get her to wake up just so she takes care of her CGM. In fact, as I've been wearing the CGM, she's been doing the opposite. Like, even here at the hotel, my alarm will go off and she'll kind of flail at me and say, hey, you need to deal with your diabetes, which I don't have. So an alarm in the middle of the night's a rare event. We both sleep better. This is going to enable more people to make the decision to loop, and it will ease the burden of setup so they're free to focus on the important thing, which is managing their diabetes. So what's next? I need to learn OTP a little bit better. I should have been at that supervision tree. I want to call it a pre-compiler because of code mash in my head, but the training session. There's a lot that I don't know about Elixir and nerves, and so I might sound like I know what I'm talking about up here, but for the most part, like, anybody could do this work with persistence and some motivation. I'd like to add support for the other CGM that's on the market, either through reading from Night Scout or from talking to the Dexcom directly. I'd like to be able to see the CGM directly on the device rather than having to push it up to somewhere in the cloud and have to look at it that way. And finally, I think the most interesting problem to solve, which is something that I don't think anybody else is doing right now, would be to have a GPS and cell connection directly on the device and have it push information up so that if somebody's on a hike and they start to go low, that you can actually send GPS coordinates to your friend and they can check in on you and make sure that everything's okay. I mean, that stuff's really powerful, which kind of leads me into what James is going to talk about on Friday. So James Smith, I think he's here. Yeah, he's going to be giving a talk at the end of the day on Friday about tracking vehicles with GPS and stuff with nerves. And so that's really cool because there's actually a parallel here for potential overlap in the things that we're doing. James and I work together. So I'm not sure. It looks like maybe it did work. Okay, cool. So that's a closed loop right there. It's setting a neutral temp basal of 0 units per hour because I don't have diabetes. But it basically did all the algorithms. That would not have shown up unless it had all the inputs that it needed in order to do a closed loop. So cool, the demo worked. All right, I think I'm ready for some questions.
I know we've got questions. So if you've got a question, come on up. We'll put you on the mic.
How's it going? Thank you. My name's Tyler. I'm actually a type 1 diabetic as well.
Cool.
I have a few questions. So, like, you talked about this loop, the whole monitor, predict, control. Is the current system, it looks like it's definitely monitoring and predicting. Is it also sending signals back to the pump to control?
Yeah, let me show you. What's your next question while I'm doing that?
What's that again?
What's your next question? Okay, so.
Oh, yeah, my next question, I guess, kind of relates to that is, I'm sure this pops up a lot in the community, but security, as far as, I have a pump, it's actually a Medtronic pump as well. Mm-hmm. What is required to talk to it as far as, can you just start changing my basal rate or bolus or stuff like that?
That's a really good question. Actually, most of this work I think was maybe founded on some security, like black hat, white hat kind of stuff, where somebody gave a talk and said, this is how you deliver a lethal amount of insulin over wireless. This pump in particular has that flaw, so all you have to know is the serial number and you can deliver a huge bolus. But for some people, having a security flaw gets turned into a feature.
Yeah,
so
definitely.
this is a risk, yes. You can basically I could sniff the data coming from your pump over wireless and know the serial number of yours. Depending on the model number, I could potentially send commands to change insulin.
Okay.
Yeah, so there's a little bit of risk here, yeah.
Yeah.
For your first question, I don't know if you can actually see it because this is hard to see, but there's like a little circle on there, and that circle basically says that I have a temporary basal adjustment, so that's a closed loop.
Awesome.
Yeah.
And then I guess my last question, which is probably the most, I think, scary from your point of view, but are you planning on sharing the code, or are you
Absolutely.
planning on?
I just gave it a name, so it's not on any of the slides. It's Infinity APS, but it's up on GitHub.
Awesome.
It's its own project, yeah.
Okay, thank you so much.
Yeah, actually, let me just go right
Probably have time for one more question. Okay, no questions? Thank you very much.
there. Thank you.